SwayamPrabha. Digital India. Educated India.
This is going to be the first lecture of week 10 of the course, where we start discussing about viscous high temperature flows. Let us see what we will do in this week. We would recapitulate concepts associated with viscous dissipation and aerodynamic heating. We would revisit concepts of kinetic theory and its connection with viscous transport phenomena like momentum, heat and mass transfer. We would look at the governing equations of high temperature chemically reacting viscous flows. Preliminary concept of radiative heat transfer would be covered, and we would have a look at some flow simulations. Starting with an overview, viscous flows, they are accompanied by very significant physical processes like viscosity, thermal conduction, mass diffusion, and these are called the transport properties of a fluid. In our case here in this course, we are primarily interested in gases, and how these processes would be affected at high temperatures becomes a major concern in hypersonic flows. And obtaining these transport properties for high temperature chemically reacting gas, of course, is a major challenge. We have to live with these challenges when we are dealing with hypersonic flow past different kinds of vehicles. Now, aerospace vehicles or devices which fly through or into an atmosphere at hypersonic speeds, they must be capable of handling the enormous heat transfer rates which are produced at those speeds. And massive aerodynamic heating occurs within the boundary layer. The viscous dissipation leads to significant heating of the aerodynamic surface, which you have learnt earlier. How we calculate the heat transfer to a surface from a chemically reacting flow field is of course a major issue. We had earlier looked at compressible boundary layer flow solution past a flat plate, but when it comes to a chemically reacting flow field moving past a surface, the solutions become much more complicated. In the compressible boundary layer solutions that we attempted, we considered it to be a non-reacting medium. Not only that, we also considered it to be calorically perfect. Therefore, in order to elevate it to the level of complexity that we are trying to address over here needs lot more effort. Shock layer in the nose region of a hypersonic vehicle can reach several thousand Kelvin temperature. Due to this, radiative heating effects are produced, and they would have to be accounted. Not only that, in the presence of radiative effects, the flow fields become non-adiabatic in nature, and therefore, we have to be careful about the formulation of the governing equations. Having looked at such an overview, we have a quick recap of the viscous dissipation and aerodynamic heating that we had looked at in the 4th week of the lecture. We are referring to content of the lecture 19 and 20, where we had attempted self similar solution of the compressible boundary layer equations on a flat plate. We solved using a pair of ODEs using the shooting technique. If you recall, we had imposed appropriate boundary conditions at the wall as well as in the far field, and we tried discussing about solution of these ODEs. The gas was considered to be calorically perfect, no chemical reactions were modeled, dissociation ionization effects at high temperatures were not considered, vibrational and chemical non-equilibrium were not accounted. So, these were the limitations which we had in the above equations. Further, the full compressible Navier-Stokes equations were not solved, they were simplified to the boundary layer form and again further simplified for the flat plate geometry. Therefore, if you want to extend the Navier-Stokes equations to more complicated geometries or flows in which viscous effects spread to much larger regions of the flow, they are not confined to a thin region next to the wall, then full compressible Navier-Stokes equations would need to be solved. That was also not done in these equations. Therefore, these equations did have some limitations. However, they still gave us some important indications. For flat plate, for example, we could work out a functional form like this for the skin friction coefficient and we could compare it with the Blasius solution and we could express it in a functional form like this, where the dependency on different non-dimensional numbers like Mach number, Prandtl number, gamma, which is the ratio of Cp by Cv, the temperature ratio between the wall and the free stream, the Reynolds number, they showed their significance. Also, the gamma was considered to be constant here, as already mentioned. The heat transfer coefficient through the Stanton number was also functionally represented and we found similar dependency on the non-dimensional numbers and we also discussed about Reynolds analogy. An interesting thing was that the Reynolds analogy that holds for incompressible flow also approximately holds for compressible flow, which was discussed. We looked at the velocity profiles for isothermal wall as well as adiabatic wall cases and we looked at the Mach number variation of the velocity profiles. In general, we found that the velocity profiles, the boundary layer thicknesses essentially go up with increase in Mach number. We found that in the laminar boundary layer case, the thickness varies approximately as square of the Mach number, and for isothermal wall, which is essentially called as the cold wall when the wall temperature is below adiabatic wall temperature, we found that the boundary layer thickness reduces and we could get the skin friction coefficient distribution for a range of Mach numbers for different kinds of conditions of temperature ratio between the wall and the free stream, and we also had a comparison with the adiabatic wall case. These distributions helped us to compute the wall shear stress or the skin friction that occurs at the wall, and as I said earlier that there was a very interesting relation that the relation Cf by 2 Ch equal to Prandtl number raised to power of 2/3 was found to be valid even for a compressible boundary layer within about a 2% variation. So, it is a good time for you to recapitulate all these facts which we left behind in the earlier week, the week 4. You may be able to recall these graphs as well, which are extremely important. The temperature profiles that typically occur in a compressible boundary layer over a flat plate and the Mach number variation, which shows that with increase in Mach number there is a very large temperature spike which can generate within the compressible boundary layer, the thermal boundary layer, so to say, and the temperatures which are reached for an adiabatic wall are way larger than the isothermal wall, and from the vehicle's thermal protection point of view, we would of course prefer to have the wall at isothermal conditions, which keeps the vehicle safe. And we talked about the cold wall case, the temperature peaks in some region of the boundary layer. Higher the temperature peak, higher is the viscous dissipation occurring within the boundary layer, and it is basically a manifestation of increase in viscous dissipation that we see through the temperature peak. Temperature peak means higher heat transfer at the wall too. We discussed briefly about the aerodynamic heating at high Mach numbers, and we said that it increases with the cube of the velocity and therefore increases very rapidly in the hypersonic flight regime. The aerodynamic drag is given by this expression, while as mentioned on top, the aerodynamic heating increases with the cube of the velocity. From the above estimates, it is evident that aerodynamic heating increases much more rapidly with rise in velocity than drag, and therefore, aerodynamic heating is a dominant aspect of hypersonic vehicle design. If we consider a hypersonic vehicle taking off from an existing runway and accelerating through the atmosphere to orbit, the major aerodynamic heating that it encounters is during the ascent phase rather than during its entry into the atmosphere. It has to accelerate significantly within the sensible atmosphere using air breathing propulsion in that case primarily, and then high velocities would be combined with relatively high density, and they would collectively produce very high heating values. So, that is of course evident from a relation like this. On the other hand, on atmospheric entry during a gliding path, which we have discussed to some extent, we will further discuss it in due course. The atmospheric vehicle will decelerate to lower velocities at higher altitudes, and this would result in lower heating rates during descent than are encountered during ascent. However, the fact still remains that at high velocities the aerodynamic heating remains a huge challenge, and therefore, when we talk about viscous flows past high speed vehicles in hypersonic ascent or entry, we have to talk about the effect of the different transport phenomena and the role that they play in the aerodynamic heating of the vehicle. When we account for those effects realistically through solution of the compressible Navier-Stokes equations along with accompanying equations to model the chemistry, then we will have a much more realistic assessment of the aerodynamic heating. We come to the very important issue of transport phenomena in a gaseous medium, which we will definitely look at in this week. The molecular transport phenomena in a gas is produced due to random motion of atoms and molecules, which we have discussed when looking at kinetic theory. When a particle, which could be an atom or molecule, moves from one location to another within the single species pure gas or multi-species gas mixture, it would carry with it certain amount of momentum, energy and mass. The transport of this particle momentum, energy and mass through the gas as a result of the random particle motion gives rise to the very important transport phenomena of viscosity, thermal conduction and diffusion respectively. And these effects manifest in a viscous gaseous medium. Therefore, in order to discuss these at length, we were waiting for this week where we have taken up the effect of a viscous medium. When we consider a gas in thermodynamic equilibrium, the macroscopic properties are uniform in space and time. Let us say the temperature, the pressure, the density of the gas from point to point within the region of interest are all uniform. However, due to non-uniform spatial distribution of some macroscopic quantities like flow velocity, temperature, the gaseous composition etc., the gas essentially goes out of equilibrium. That means, between two different points you may see a variation in velocity or temperature or mixture, gas mixture composition would essentially mean that it is going out of equilibrium, and due to this non-equilibrium additional phenomena arise as a result of the microscopic molecular motions which are going to follow consequently. The consequence is that molecules in their random thermal movement from one region of the gas to another, they tend to transport with them the macroscopic properties of the region from which they come. If and when these macroscopic properties are non-uniform, the molecules thus find themselves out of equilibrium with the properties of the region in which they arrive. The result of these molecular transport processes is the appearance at the macroscopic level of the non-equilibrium phenomena of viscosity, heat conduction and diffusion. In due course, the transport processes tend to establish equilibrium. So, this is essentially the background that we are trying to discuss and elaborate further. So, it all gets triggered from non-uniform spatial distribution of some of the macroscopic quantities, which throws the system out of an equilibrium and sets in the non-equilibrium effects, which finally lead to the viscosity, heat conduction and diffusion playing a role in the transport processes. Now, when we look at the phenomena from different angles, there is a macroscopic cause. We say that there is non-uniformity in either velocity, temperature or composition, which we were just talking about a few seconds back. The associated molecular transport, which we would try modeling using kinetic theory later. The molecular transports are associated with momentum, energy and mass, essentially transport of momentum, energy and mass, and the macroscopic results are nothing but viscosity, heat conduction and diffusion. So, we have a nice matrix here where we see the connections essentially, and this could be a good time for us to have a quick recapitulation of some of the concepts of kinetic theory that we saw earlier, and this quick recapitulation will help us elaborate on this transport phenomena model further in the next lecture. We recall from lecture 32 where we talked about the kinetic theory, and we imagined a kind of box like region within which the gas particles were allowed to move around, and we saw that as they move around they could have different components of velocity along the orthogonal directions. We named them as Cx, Cy and Cz here, and we tracked the movement of those particles. If we were tracking them over a short time interval during which the particle did not collide with any other particle, but it collided with a wall of the container, then we would find the reflection of the particle happening specularly from the wall, and we tried to explain how the specular reflection happens through these equations, and we had an accompanying diagram to help our understanding in this way, and such specular reflections can happen in other planes too. Now, as such reflections from the wall happen due to collision of the particle with the wall, there is a momentum change which would occur. So, if you look at the momentum of the particle which was approaching the wall with Cx velocity, this would be the momentum before the collision, while after collision, once it rebounds specularly, the momentum of the particle is given by this equation, and therefore, there is a change in momentum along the x direction, which was given by this equation. As the particle traverses the x direction with velocity magnitude Cx, it would perform the following number of complete to and fro traverses of the box length L along the x direction in unit time. So, we obtained the number of complete to and fro traverses of the particle as we tracked it, and therefore, the time rate of change of momentum of the particle when impacting the right face could be computed. It was the momentum change per collision into the number of collisions per unit time, which we computed, and it came out to be a form like this. And from second law of Newton, the above would be equal to the force acting on the right face of the box due to the above particles collision during unit time. That gives rise to the pressure, which is nothing but force per unit area. So, we obtained the expression for force through the time rate of change of momentum in this equation, and then we divided by the area, which is nothing but the area of that face of the box, the right face of the box, and therefore, we came up with an expression like this for pressure. Now, in this expression, the V is the volume of the box, which comes from the L cube term, and we have been discussing about only one particle colliding with the right wall. However, in reality, a large number of particles are confined in the box, and we need to account for them too when they are colliding with the right wall. Let us assume that particles with mass mi and velocity ci are entering into such collision. Then the pressure exerted on the right face by all the particles would be given by an expression like this, where we sum up the effect over all such collisions, and by virtue of the particle movement between the right wall and the left wall, they are colliding with the left wall as well as frequently as the right wall, and hence an equal pressure is felt on the left wall too, as is given by this equation. From that concept, we can extend it to saying that in a similar manner, the pressure is exerted on the front and rear walls too, where we account for the y component of the velocity of the particles. When it comes to the top and bottom walls of the container, then we account for the z component of the velocity, and thereby we are talking about collisions which occur through the particles moving along either x direction or y direction or z direction on an average, and giving rise to pressures on pairs of walls like this. So, if we add three equations, we get a measure of the average pressure felt on the walls of the box due to these particle collisions. So, we essentially sum up the pressures and come to an expression for 3 times P, and we also sum up the resultant velocities essentially of the particles, where all the 3 components x, y and z participate, and they effectively give rise to the resultant movement, which effectively connects with the first diagram that we showed in the box form, where each particle was having different components of the velocity, and therefore, the final average pressure expression accounts for the magnitude of the velocity. From the equation that we derived, total kinetic energy of the system of I particles can also be obtained. by virtue of their translational motion. We define it in this form, and by combining the pressure equation and the equation for kinetic energy, we get P times V equals 2/3 E dash translational. This is the kinetic theory equivalent of the perfect gas equation of state. This equation is applicable when the calculations are done on unit mass basis. When we do it on a per mole basis, then we have to involve the molar volume and the kinetic energy per mole, which becomes E translational. We remove the dash in the expression, and therefore, the equation becomes like this. We move on, and since the equation of state on mole basis can be written in a form like this, where the universal gas constant gets involved, the E translational is 3/2 RT. This incidentally is the same result as we had obtained earlier in statistical thermodynamics, where this is what we had visited, and there we had done it using a partition function approach. Now, since in kinetic theory we are dealing with particles, we would like to obtain the expression for translational energy applicable on particle basis, and therefore, we introduce the Avogadro's number N A, from which the mean kinetic energy of a particle can be obtained by introducing the Boltzmann constant K. Later on, you will see that the thermal conductivity also has to be brought into our discussion, where we would have to figure out an alternative nomenclature system. This temperature is a direct measure or index of the mean kinetic energy of a particle in the system, and the product P V is essentially a measure of energy. So, these were very interesting and important concepts that we introduced through our discussion of kinetic theory basics. And then if we return to the equation for average pressure and divide it by the total mass of the system, which is here, we end up getting a form like this. From the above equation, we derive the definition for mean square velocity of the particles. So, this is the nomenclature for the mean square velocity. Also, by definition, the ratio m by v, which figures over here in a reciprocal form, is essentially density. Hence, we can write P by rho is 1/3 C bar square. Again, perfect gas equation of state can be written in the form P is equal to rho RT. Hence, comparing the two equations, we are able to show that C bar square is 3 RT. The root mean square velocity of particles is of course given by taking an under root of the C bar square, which becomes under root 3 RT, and revisiting the E translational equation, which is nothing but the mean kinetic energy of a particle, we can show that it is the E translational is equal to 3/2 kT. Since E translational is directly proportional to T, higher the value of temperature, higher is the mean particle kinetic energy, and vice versa. It is independent of the mass of the particle. All particles which reside at the same temperature would essentially carry the same translational energy. The expression C I is equal to under root 3 kT by m I tells us that at a given temperature T, the heavy particles will on an average move more slowly than the lighter particles, which is a very important fact. Therefore, there would be a velocity distribution based on the mass distribution of the particles. When it comes to particles interacting with each other, we talked about the sphere of influence, and there we said that the particles actually do not physically collide, but they come in proximity with each other, and the sphere of influence is what sets them apart. This is the so called billiard ball model that we talked about. So, the sphere or radius of influence is what we tried to discuss over here, and then we talked about the actual movement of particles through the gaseous medium, where their trajectory is essentially defined by the sequence of collisions that they undergo, and they may typically go through a route like this, where we have tried pointing some of these dots where the encounter with other particles took place through collisions, which we hypothetically represent in a form like this, where as though the particle or the molecule is translating at c bar velocity without collisions taking place. The radius of influence of the molecule sweeps out a cylindrical volume per unit time as it moves through the gaseous medium. It is given by pi d square times c bar, and if number of particles, which could be atoms or molecules, per unit volume is n, where n is nothing but the number density, then the above particle encounters n times pi d square c bar collisions per second. This number is called as a single particle collision frequency, which we give by z dash. The mean free path is the mean distance travelled by a particle in between collisions. It was shown as lambda, which is nothing but c bar by z dash, and it came out to be n pi d square. And all that we discussed over here is based on a simplified model, where the moving particle encounters other particles, which incidentally just lie on the path. We do not consider that the other particles would also be moving, and they would also be having their own velocities, in which case the relative velocity has to be accommodated. We also discussed a little bit about that in a later lecture, but which we may not have time to discuss about over here due to paucity of time. Therefore, we come up with the conclusions here, and we will discuss about more of the kinetic theory in the next lecture as and when we would need it. So, in this lecture we recapitulated the concepts associated with viscous dissipation and aerodynamic heating from the compressible boundary layer solution on a flat plate. Subsequently, we recapitulated the concepts of kinetic theory and its connection with viscous transport phenomena, the phenomena of momentum, heat and mass transfer. This aspect would be further elaborated in the next lectures. Thank you.